Here we go, Chapter 3, Section 2. This one's going to be split up in two different lectures. And this is, we're going to pretty much stop right here. No, that's not true. So a regression line is a model for data. The same way that we use the normalized curve to allow us to make predictions about the location of things, probabilities, areas, percentiles of particular data as it relates to a data set that is so symmetrical and uniform and unimodal that we feel like the normalized curve is a good model for it. If there's a strong enough correlation, then a regression line is a great opportunity for us to use that model to make predictions about outcomes or given a change in the explanatory variable. Of course, because it's statistics, we can take it's going to look a little different from what we're used to. So a line, we're used to having y equals mx plus b, where m stands for the slope, and then b stands for the y-intercept. Of course, because it's got to be confusing, we're going to go ahead and recognize that statistics looks at a couple of different things. For one, whenever we're using a predictive model, there's going to be this little hat on it. And the y, which is normally the outcome, we read this as y hat. And that's the predicted value of the y when we're using our model, when we plug in the x. So when we find what we expect it to be based on our model, then we use y hat. If we look at the actual data point at that x, then we're talking about y. So y hat is a prediction based on a model, and that's a very important distinction. So for reasons I do not know, b is the slope and a is the y-intercept. You know what slope means. It's really important that you can interpret what that slope is given the context, and so you might choose to practice some more problems than the ones that we're going to see in class. So once we decide that a linear model is appropriate, this is obviously showing a negative linear association. I would guess around a 0.7, negative 0.7 r, but that's just me guessing. A regression line can be created. And a regression line is made by finding the least squares of the residuals. We're going to talk about that in a couple of moments. But this particular one has modeled it where the price, and notice the price is wearing the little hat saying it's the predicted price based on the model, is the $38,257 minus 0.1629 times miles driven. They kind of wrote all over it, so it's kind of hard to see. So what we're going to want to be able to do in all situations where we have a regression line is to be able to interpret the parameters, the slope and the y-intercept, and then of course use that regression line to make some predicted prices in this case, or predictions based on what we would expect. So in this case, the slope, which is right here, you guys recognize that it's always the one in front of the variable. The variable in this case is defined right inside there as opposed to an x or something like that. They've written miles driven as your x in the equation. That's pretty common in statistics to do it that way. So what is the 0.1629? It means that for each mile that has been driven by the Ford, it's going to drop about 16.29 cents. So it's going to be a drop, you can tell, because it's a negative slope and it's a negative slope there, that it's going to drop by about 16.29 cents per mile. And the y-intercept is the predicted price of a Ford 150 that's been driven 0 miles. Now remember that the y-intercept is not always based on the situation, an actual number that makes sense for the situation. In this case, we are starting pretty close to 0, so that could be an actual good prediction. So we can use a regression line to predict the y-hat, predict a possible value, and so we can use the regression line visually. It's pretty easy to do. You go ahead and find where they meet, but we should use the equation to find an exact answer. So if we wanted to find the price we would expect, predict at 100,000 miles, we would just replace 100,000 miles in for miles driven, do the math, and find that we would expect it to be about $21,967, which we can eyeball right there, same. So we're talking here about extrapolation, and extrapolation is the idea that you are going to try and use the linear regression line to predict for values of x that are way outside of where the data was taken. For example, our cars in the previous slide, we had information from about 10,000 miles driven to about 160,000 miles driven, and so we can go ahead and use that regression line to make some predictions. Later we're going to find out, some metrics to decide how accurate of a prediction they are. But once we start going outside of where our data is, it's called extrapolating. So predictions outside of where your x values are coming are not accurate. For example, we can easily, since it started around 10,000, our data, we could probably make some accurate predictions around $5,000, but we really couldn't make very accurate predictions if the car had been driven 250,000 miles, because we have no data on that. It's actually physically possible that if you ran 250,000 into this linear regression model, we might find out that the car is in negatives, and it just wouldn't make any sense. When we as statisticians create a regression line, the goal is to make the distance from the data points to the line as small as possible. And a good regression line, the best regression lines are the least squares regression lines. So the squares of the residuals are as small, the sum of those are as small as possible. But residual itself is just the idea that we're going to look at the actual data point versus what we would predict from the regression model at that x value. So we take the actual data point and subtract it from what the model predicts, and that's your residual. We want those residuals to be as small as possible. Sometimes residuals will have a negative value because it's below the line, and sometimes residuals will have a positive value because it's above the line. So we're going to talk about how the least squares regression line comes to be the best line of fit. And there is going to be, once again, what statisticians often do to offset positive and negatives canceling each other out is to square them. So for example, if we looked at this residual right here and this residual right here, they're very similar in their distance from the regression line. And so if I were trying to find the least sum of the residuals, these two would cancel each other out and make it look like the line was a better line than it actually is. So instead of just looking at the distance, the statisticians look at the square of that distance, okay? And we're looking to create the line that has the least squares possible, or the sum of the least squares possible. And so here is a bigger example of the squares on this particular line. And if we move the line up a little bit, it would create bigger squares down here. We're going to spend some time with a model that will help us to see that. But the idea is we want the smallest square, smallest sum of the squares of the residuals possible. So this section basically had us look at the least squares regression line and using it to understand a situation better. So when you are looking at these things, make sure that you can interpret the slope in context, tell what that slope means for this particular situation, what the y-intercept means in this particular situation. And you should be able to plug in a value for x and make the prediction. Remember that prediction is a y hat as opposed to the y that is the actual result at that particular one. The difference between those two is your residual. The difference between the observed and the prediction is the residual, and we'll talk about standard deviation in the next section. And then you should understand how the best line of fit is found, which is by taking the residuals and squaring them and finding the line that gives you the smallest sum of those squares. These other four things we will be doing in the next section coming up, which talks about determining those equations using technology, and deciding if a linear model is appropriate using a residual plot, the same way we decided if a normal model was appropriate by looking at a normal probability plot. We're looking for a straight line, if you remember correctly, from the normal. And then we're going to look at some metrics to decide how accurate of a model is it, and some other components that help us to look at outliers and how they're affected. So that'll be coming up in a couple of days.